Welcome to Chapter 4, Periodic Table, which I predict is going to be our quickest review video. The front loading of this chapter, right, the first half was a lot of terms. There was a lot of stuff you had to know. And the back end of the chapter was taking all that stuff we had to know and then doing the conceptual piece of it, which was applying some concepts like Coulomb's law to the periodic table and trying to predict how and why certain properties of the elements change the way they do. So let's get the terms out of the way first. Groups are the columns going up and down, also known as families. Elements in the same group have the same number of valence electrons and therefore same chemical properties, or similar chemical properties. Periods are the rows going across from left to right. They tell us the number of energy levels or shells in an atom. Periodic law is the idea that properties of the elements are functions of their atomic number. It's the idea of periodicity, meaning that if we start at group 1 and travel left to right all the way to group 18, when we come back to the next row of group 1 again, we're going to see the way that the properties change across the period. When we start up again, we see that repeating change in those properties. Elements in our current periodic table are arranged in order of increasing atomic number. That was thanks to Henry Moseley. But Dmitri Mendeleev is known as the father of the periodic table because he was the first person to construct such a table that showed the true periodic nature of the elements. Remember, he arranged them by increasing atomic mass, but he gets so much credit because in his table he left gaps for elements he said that were not yet discovered, and then predicted properties for those unknown elements by looking at how the properties change and how the properties of the elements to the left and right and top and bottom of those empty boxes compared. And then when those elements were eventually found, they matched his predictions almost to a T. It was really, really impressive at the time. So he's known as the father of the periodic table, although Henry Moseley then corrected the minor imperfections in Mendeleev's table. You should be familiar with the specific groups that we focused on throughout the year, group 1, 2, 3 to 12, and then 17 and 18. Know them by name and know their important properties that are listed here that we went over. The metals are to the left of the step or the staircase. They make up most of the periodic table. They tend to lose electrons to form positive cations. They have low ionization energies and electronegativities, which we will get to in a moment. Good conductors of electricity, high melting point and boiling point, hard, malleable, and ductile. Metalloids are found along the step or the staircase, also known as semi-metals. They have properties of both metals and nonmetals, right, like being a semiconductor. The elements listed there are the metalloids. Polonium and astatine are radioactive, so some sources consider them to be, some don't. The first 6 there are the most important ones, so that you understand where the step is. The nonmetals are to the right of the step. They gain electrons to form negative ions. They have high ionization energies and electronegativities. They're poor conductors of electricity. They have low melting points and boiling points, and they tend to be soft and brittle. There are 7 really important elements to know as being diatomic, meaning they exist as 2 of their atoms bonded together in a molecule. Those are the Brinkelhoff elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. You should be familiar with the states of matter of all the elements at room temperature. Most of them are solids. There are 2 liquids. The metal liquid is mercury, the nonmetal liquid is bromine, and then we have the gases, which are the noble gases, plus nitrogen, chlorine, hydrogen, oxygen, fluorine. Everything else is a solid. So if you know the liquids and gases, you know the solids. You should be familiar with how to read each of the boxes in the periodic table, right? Most tables give you the symbol. Ours does not have a name because we memorized the names and symbols of the elements, but some of them do. You have the atomic number, which is telling us the number of protons, and then the average atomic mass. And then the second half of the periodic table chapter was focused on looking at these specific properties of elements. The first thing we did was look at Coulomb's law, because really that was the justification we gave for why atomic radii, ionization energy, and electronegativity changed the way they do across the table. Coulomb's law is the idea, it's an equation that we can use and you will use in physics to calculate the amount of electrostatic force that either attracts 2 bodies together or repels 2 charged bodies. In our case, what we're looking at is the attraction of the positive nucleus to the negative electrons. And the important things that we need to know is that the attraction between those oppositely charged bodies increases when either the distance between them decreases, right? So think about two magnets holding opposite ends. You're going to feel the attraction more when they're closer together. The other way to increase the Coulombic attraction between two charged bodies is to increase the charge of either one. Either make it more positive or more negative, doesn't matter. But increasing the charge on either body or shortening the distance of attraction will increase the Coulombic attraction. Having said that, we then went to look at atomic radii, ionization energy, and electronegativity. So atomic radii is essentially the size of the atom, right? It's the radius of the atom of an element. And we see that it increased going down and decreased going across. Now again, knowing how they change across the periodic table and down the periodic table is important, but justifying it is equally as important. So going down the periodic table, we have an increased number of shells that just makes the atom larger. The increased distance of the valence shell to the nucleus decreases the Coulombic attraction. Going from left to right, the atomic radius decreases because we are adding more protons to the nucleus, making the nucleus more positive, more positive, more positive, and we have the same number of shells going across a period. So the valence electrons are about the same distance from the nucleus, but we're making the nucleus more positive, which allows the nucleus to pull that valence shell closer to itself because of the increased Coulombic charge and attraction. So that's the justification there. If we understand the rationale behind how atomic radius changes, then we can just blame atomic radius for the changes in ionization energy and electronegativity. Ionization energy, remember, is the energy needed to remove an electron from an atom. So the more energy is needed to remove an electron if the valence electrons are being held tightly to the nucleus, meaning the Coulombic attraction is strongest on them. So the smaller the atom, the higher the ionization energy is going to be, because the nucleus is pulling on the valence shell more. The larger the atom, the lower the ionization energy is going to be because the nucleus is pulling on the valence electrons less because the atom's larger. Electronegativity is not measured in a specific unit. It's just a ranking. We have a scale of from 0 to 4 that describes the ability for an atom to attract electrons to itself in a chemical bond. Fluorine is designated with the highest electronegativity of 4, and then all the other elements are ranked based on fluorine. Again, what we're looking here to, in order to justify this, an atom can add an electron to its valence shell if the nucleus has a strong attraction for an incoming electron. Fluorine, being a super small atom and having not many shells, will willingly take electrons because the incoming electron will be super close to the nucleus, and that nucleus has a really high nuclear charge because there's a lot of protons in it. If we go all the way to the other side of the table, like cesium and francium, down in the lower left, those atoms are really large. Their effective nuclear charge, or the Zeph value, is not great. It's +1. And we'll talk about shielding and Zeph in a moment. The atom is large, though, which means an incoming electron is going to be far away from the nucleus. That nucleus is not going to have a good attraction or make a good attraction with that incoming electron. Zeph, remember, was the effective nuclear charge. The nuclear charge is basically just how many protons are in the nucleus, but the core electrons cancel some of the positive charge of the protons. So the effective nuclear charge, or the Zeph as we abbreviated it, was the net positive charge that the valence electrons feel. So essentially, if you take the number of protons in the nucleus and you subtract the number of core electrons that are canceling out the charge, you're left with the Zeph value, or the effective nuclear charge, or the net charge that the valence electrons are feeling. And the idea of shielding, which changes in the table going from left to right, is the core electrons are getting in the way of the nucleus's attraction for the valence electrons, right? So if we look in the table, going, I believe I just said it changes left to right, but that is not correct. The shielding is constant there because the core electrons are staying constant. Shielding changes going down a group, because if we think about going from lithium to sodium to potassium, we are adding electrons to another shell of the atom, so we're increasing the number of core electrons between the nucleus and the valence electrons, and that is increasing the shielding effect. The more core electrons that are between the nucleus and the valence electrons, the more shielding is going on, preventing the nucleus from attracting those valence electrons. The only other thing we really looked at was in terms of neutral atoms becoming ions, cations if they're losing electrons and anions if they are gaining, was how the size of the atom changes. If an atom is losing an electron, then the size actually becomes smaller. The cations are always smaller than the neutral atoms from which they form. Because once an electron is lost, now that ion has the same number of protons pulling on fewer electrons, and they can pull each of those electrons more efficiently or effectively to the nucleus. If a neutral atom gains an electron, now the ion has the same number of protons trying to pull more electrons, and they cannot pull that extra electron as efficiently as they were before it was in the shell. So anions are always larger than the neutral atom. We previewed very briefly what we're going to see in the next review video, which is bonding. After those ions form, they will come together to form an ionic compound, but we'll save that for the Chapter 5 review video. So this brings us to the end of Chapter 4, Periodic Table, and you should be now ready to take your Chapter 4 throwback quiz.